Okay, 4.1, we're solving polynomial equations. No different from the last chapter, we're using factor theorem to solve for the unknown variable. Okay, solving polynomial equations, we're using a variety of strategies. Basically, we're using what we learned in chapter 3 to solve word problems. Amelia's family is planning to build another silo for grain storage identical to those that they have on their farm. The cylindrical portion of those they currently have is 15 meters tall, and the silo's total volume is 684 pi m cubed. Okay, don't think of pi as a variable. Okay, it's just a constant. Okay, we all know 3.14 is just going to be multiplied by the 684. Okay, so please don't think of that as a variable that needs to be solved for. It's not. So what's the possible values of the radius for the new silo? So we should know that our volume for a cylinder and our volume for our sphere. Okay, we need to know those formulas. Cylinder is an easy one. It's just pi r squared times height. So the area of a circle times its height. And that 15 meters is given from the question. 15 meters up here. It's 15 meters tall. The second part, the volume of the sphere, because it's a half sphere, a hemisphere, we do 1/2 the formula for a sphere, which is 4/3 pi r cubed. Okay, then we do some simple multiplication. We multiply the half and the 4/3, we get 2/3 pi r cubed, and then we substitute the 15 in for the height. Okay, and all of that is equal to 684. Again, that's from the problem that's given. Okay, so we have this equation here, and we call this a polynomial equation. Okay, and it's basically an equation in which one polynomial expression is set equal to another. Okay, remember a polynomial expression can still just be a constant, which it is on the left-hand side. So like we've been doing for a couple years now, we want to kind of move everything over to one side and set it equal to 0. So that's what we're doing with the 684. Traditionally, we move to the left-hand side. Everything's already on the right. And we like to keep the coefficient, the leading coefficient of the highest degree term, positive. That's why we took this 684 and moved it to the right. Okay, so we have this expression, which is the same as equal to 0. Any questions there so far? All right, once we have that set equal to 0, the next thing is we want to factor out anything that's common. Should notice right away that the pi is common. And then we factor out 1/3. And the only reason we do that is so that we don't have to worry about the fractions. We can deal with whole numbers. Okay? So when we factor 1/3, we're basically just multiplying everything by 3. That's why the 15 becomes 45. And the 2/3 becomes 2 because we're multiplying by 3. Right? That's to get that third out. And the 684 becomes 2052. And the pi is factored out. Any questions to there? Right. How can you verify the solutions you found with and without using a graphing calculator? Well, we haven't found any solutions yet, but one way we might do that with a graphing calculator is just to verify that those radiuses are actually crossing the x-axis at 0. Okay, if we're setting everything equal to 0, we're setting this whole expression equal to 0. If we get answers for the radius, we have to sub it in and verify they equal 0. Okay, that's how we could do it algebraically without a graphing calculator. With a graphing calculator, we would just look on the graph and make sure that those radius values are equivalent to 0 on the y-axis.
So I think you missed a page. You skipped a page. Yeah.
Oh, did I? Oh, that would make sense. All right.
Yeah.
Thanks. We'll get there. Okay, so that made sense. That's why we hadn't actually solved them yet. Okay, so we have everything equal to 2. Sorry, we have everything set equal to 0. The next step is that we need to rewrite in descending order. So this r cubed needs to come in front of the r squared. You guys see that okay? R cubed in front of the r squared. So it gets rearranged. And finally, the next step is that we need to use factor theorem to guess and test to see what our first factor is of this trinomial. Okay? So remember it has to be multiples of 2052. I didn't mention this last chapter, But the way the multiples work, because in last chapter we hadn't had any leading coefficient terms, or they were always 1, the multiples that you need to guess and test are actually multiples of this value over multiples of this value, 2. Okay? So the first one, you can consider that the multiples of 2 are 2 and 1. So you consider multiples of this 2052 over 1 initially. I'm going to talk a little bit about that later in this chapter. Okay, so if you're not quite understanding that, I'm going to show you a little bit later. Okay, it'll make more sense. But for now, we can check all the multiples of 2052 over 1. First one we check is 2, then 3, and then 6. And we find if we check f at 6, we get 0. So there's our first factor. So therefore, by factor theorem, r minus 6 is a factor. Then we use synthesis to find out what the resulting trinomial will be after we divide out r minus 6. So we get this term. This term cannot be factored using inspection. Why? Because we can't find, it's not a whole number that multiplies to this and adds to this. Okay? You guys remember that from grade 11? Sometimes we can't use M&A or we can't use inspection. We have to use the quadratic formula, okay, which is here. Okay? Yep, so it does still happen. Okay, once we use the quadratic formula, we find out the two values of r are negative 8.6 and negative 19.9. Yeah, Marco?
Sir, from the equation of pi over 3 in brackets 45r squared plus 2r squared, and then you go to 0 equals 45r squared, where did the pi over 3 go? In the page before?
The page before?
Yeah, that bottom equation.
Yeah.
Pi over 3, and then the next page, pi over 3 is gone.
Yeah, so you multiply everything, both the left and the right side, you can divide it by pi over 3, right? So if I do this, divided by pi over 3, divided by pi over 3, these go away, and 0 divided by pi over 3 is 0. So it just goes away. Okay? Yeah, it's like any constant. You can just factor it out, and then because the left side is 0, the constant just divides off, okay? Good question, though.
Yeah, but how would you find out that there's a pi over 3 there? If you want to read like...
Because it's common. See, the pi is coming here. Pi, pi, pi. And then we want to get rid of the fraction, so we divide by a third. Or multiply. Divide out a third of each value. Okay?
How would we go back? If you're trying to go back.
What do you mean?
Okay. Don't need to go back.
You don't want to go back. You want to keep moving forward in life there, Raymond. All right. So we end up with two negative values for our radius. That's a problem because as we know, we can't have a negative value for radius. So these two values are invalid for us. So we know the silo must have a radius of 6. Okay? And where does that 6 come from? It comes from the original factor that we guessed up here. Okay? And I say we guess it because we did guess. We guessed the multiple of 2052 here and plugged it in and got 0. Okay? Any questions? Yeah.
Okay, so say we do the quadratic formula and we get a positive, then what do we use? Then what happens?
And we get a positive here?
Yeah.
Then there could be two values. It could be two answers. Let's say this was a positive 8.6, then you would say the possible radiuses of the silo are 6 and 8.6.
Oh,
Okay?
so there's not like one.
No, they could have the same volumes, right?
Okay. Yeah.
In this particular example, they can't because we solved it, but in some examples, you might have two different answers that are both valid. So how could you verify the solutions you found with and without a graphing calculator? With the graphing calculator, we could graph it and then ensure that those radius values, which are here, 8.6, negative 8.6 is negative 19.9, and positive 6, all cross the x-axis. The y value is 0. Without a graphing calculator, we could take these values and plug them into the original equation, which is back up here, and make sure we get 0. So if we plug in negative 8.6 into this equation up here, we should get 0. Okay? That's how we could verify it. What restrictions was placed on the variable in the polynomial equation? Explain why this was necessary. What restriction did we place on the radius r? Yeah. Yeah, it's got to be positive. Perfect. Why? Because we can't have a negative dimension. Do you think it is possible to solve all cubic and quartic equations using an algebraic strategy involving factoring? What do you guys think? Anybody? What do you think? The only reason we were actually able to solve this with the quadratic, so someone might argue, yeah, you can definitely do it because you can always use the quadratic. The only reason we were able to use the quadratic is because one of our factors worked originally. Okay, that doesn't have to be the case. Okay, it's possible that you can plug in all these values and not get any whole number factor. If that's the case, we cannot reduce it from a quartic or a cubic, and then we don't have a quartic or cubic equation. We only have a quadratic equation, right? Or a quadratic formula, sorry. Okay, so if we can't reduce it from this cubic, then we can't use the quadratic and we can't factor it, we can't solve it, okay? There probably is an equation like this for cubic and quartic functions called the cubic equation, and the quartic equation is just beyond the scope of this course, okay? So we won't be factoring those. All right. Example 2, solve 4x cubed minus 12x squared minus x plus 3. So the first solution uses factor theorem. So what is factor theorem again? We set everything equal to 0 and we guess and test. The variables we're going to test are going to be multiples of 3 over multiples of the leading coefficient of the highest degree. So this is what I was talking about in the last example, okay? So in the previous chapter, I mentioned to you guys that the guess and test values are multiples of the last constant here. Okay, now I'm kind of rewording that or adding to that and saying that they're not actually multiples of the last constant. They're multiples of the last constant over the first coefficient. Okay, that's what this is. P over Q. Okay, P is a factor of the constant term 3, and Q is a factor of the leading coefficient 4. So just like in chapter 3, we still use all the factors of 3, so 1 and 3, plus or minus 1, plus or minus 3. But in addition to those factors, you're going to check those factors over the factors of 4. So we get plus or minus 1, plus or minus 3, plus or minus 1 over 2, because 2 is a factor of 4, plus or minus 3 over 2, again, because 2 is a factor of 4, and plus or minus 1 and 3 over 4. Any questions about that?
Can you repeat that?
Okay, it's a lot to repeat, but the numbers that you guess and test with for factor theorem are not just multiples of the last constant, they're multiples of the last constant over multiples of the first coefficient, the leading coefficient. Okay? So these values here should make sense to you. Okay? The denominator is always a multiple of the leading coefficient. In this case, it's 1 over 1 over 1. We don't write it. So the multiples of the leading coefficient are 1, 2, and 4. 1, 1, 2, 2, 4, 4. The multiples of the constant are 1 and 3. 1, 3, 1, 3, 1, 3. Okay? Make sense? So it's the numerator are multiples of this, and the denominator are multiples of this. Okay? How would I test it? How would I still use factor theorem? I'm going to still always consider the multiples of the constant first over 1. Okay, I'm still going to test 1 and 3. And of course, look, 3 works. So it didn't even matter in this case. But it's important to know that if those two don't work, just the multiples of the constant, you have to check the multiples of the constant over the multiples of the leading coefficient. But always, always start with 1, -1. Start from the bottom. Okay? By the factor theorem, then x minus 3 is a factor of f at x. So we found it. It was 3. So remember, the factor is the reverse sign. You do x minus 3. Why is it x minus 3? Because that's going to be a factor. You set it equal to 0. So x equals 3. That's why. Okay? So then we divide. You could have done this by synthesis. They used long division. And they got this. 4x squared minus 1 is left. This you should recognize right away is actually 4x squared minus 1 squared, which is a difference of squares, right? So 2x okay, so there's our fully factored equation. Now to solve the zeros for this, you set each one of these equal to 0 since the whole expression is equal to 0. So we have 2x minus 1 is equal to 0, 2x is equal to 1, x is equal to 1/2. This one, x is equal to -1/2, and this one, x is equal to 3. So there are our zeros. Any questions with that problem? Now there is an easier way. If you would have recognized at the beginning. Okay, so this is what I've just done here. And then this, they're just checking by plugging in those values and making sure that they get 0. And there's the answers, which we solved on the last page. The easier way, if you would have recognized the first two terms and the last two terms, could have been group factored. So what's common between these two terms? It's 4x squared. You're left with x minus 3. You factor out minus 1 here. You're left with x minus 3. Then you factor out the x minus 3, and you're already done. No factor theorem was necessary. No long division. You went here right away in one step. So that's why it's important to always look for the shortcuts. Look for factor by grouping. Look for anything that's common that you can factor out before you start. And then they get the answers much quicker. Okay, just 2 steps. Alright, example 3. The path of 2 orcas plane. Who wants to read? Marco, go ahead. Right here.
The paths of 2 orcas playing in the ocean are recorded by some oceanographers. The first orca path could be modeled by the equation ht equals 2t to the power 4 take away 17t to the power 3 plus 27t to the power 2 take away 252t plus 232. And the second by ht equals 20t to the power 3 take away.
It's exponent. Careful, it's exponent of 3. The whole term is a power. The 3 is an exponent.
20t to the power 2 plus 30t take away 20. There, where h is their height above and below the water surface in centimeters, and t is the time during the first 8 seconds of play. Over this 8-second period, at what time were the 2 orcas at the same height and depth?
Okay, good. So when you are reading mathematical expressions, this would be not t to the power of 4. This whole thing is a power. This is an exponent. This is a power. And this is the base. So when you read it, it would read t to the exponent of 4. If you read it t to the power of 4, that doesn't make any sense. So just be careful with that. So we have 2 equations, one for one orca here and one for the other. So they're jumping in and out of water. So we're expressing the height of their jump above seawater with relation to time. So it asks, over this 8-second period, what times were the 2 orcas at the same height or depth? So we want to set the heights equal to each other. And then if we do that and solve for t, we can figure out the time that they're at this, same height. Does that make sense? So it's a really long equation here, but it's not too bad once you start working it out. So we set one of their equations equal to the other. So that's what we have here, is equal to this. Any questions why I set those equal? Because that's their height, right? So they're the same. Now I rearrange and put everything to one side, and I order all the exponents in decreasing order. So I put the exponent of t to the 4 at the front. Then the next thing I say, well, I'm going to make a new function now that I let the equation f of t equal this. So this is the function of both orcas, and I'm going to solve for my value of t. Okay, so my possible values of t to make f of t 0 are the multiples now. It's unfortunate this is on the other page, but it's the multiples of 432 over the multiples of 2. Okay, so what values go into 432? 1, 2, 4. And then they have to be over the values of 2. So 1 over 2, 2 over 2, which again is just 1. 4 over 2, which is a half. Okay? So all of these multiples over all the multiples of 2. Starting off over the multiple of 1, and then over the multiple of 2. Okay? But I can start with checking the whole numbers, because they're over the multiple 1, right? Lots of different numbers going to 432. We can see them all here. Plus or minus 1, plus or minus 2, 3, 4, 6, 8, 9. I'm sure there's others. Test 1, we get 72. Test 2, we get negative 28. 3, negative 18. 4, finally we get it is 0. Okay? Again, very, very, very useful to figure out how to use your calculator. If you have some time and someone has the same calculator as you, or you're doing your homework and you want me to try and figure it out, it's very valuable for you guys to be able to enter this expression, which is relatively long here, and then just plug in different values of x. It'll be very, very quick to figure out the value that you need to obtain 0. Okay? Some of you guys even have calculators with a table function. You can do that very quick. Okay, next, by factor theorem, t minus 4 is a factor then. Okay, we know that because when we sub in 4, we get a result of 0. We use synthesis, so we put the coefficients up top, and then we drop them down. Multiple by 4 is 8. Add these two, negative 29 times 4 is negative 116. Add these two, 111. We do everything, we get a remainder of 0. These now become the coefficients of our quotient, or our divided term. Next, we have to use factor theorem again. Why? Because we still have a cubic function. We still have this value of 3. So we need to use cubic function again. Sorry, factor theorem again. So we sub in 6, 8, and 9. When we go to use factor theorem again, don't start at the beginning because you've already tested those numbers. Okay, so just like 3 goes into 27, 9 goes into 27, you're not going to test 3 again. Okay, so it's the same idea. You're not going to go back and test from 1 again. You're going to keep going from 4. You're going to test 6, 8, and 9. Okay, when you're testing the second factor theorem, you're going to keep going from up above. Okay, you won't get any values below there again. So they find out that 9 use synthesis again. We find 9 by factor theorem. We use synthesis again. And we end up with this equation, okay? We factored this by inspection, which gave us those two terms.
Sorry for interruption at this time, teachers. We are asking that all grade 10 students who received letters regarding the awards night tomorrow night, can you please come down for a brief meeting in the mini-gym. That's again, all grade 10 students who receive.
Okay, so then our values then are t equals 4, t equals 9, and t is 1/2. So these are the times then that the height of the two orcas are the same. Any questions? So factor theorem twice in this. Both times, even though we did have a leading coefficient, we still only looked at, we had a leading coefficient in the first one as well as the second one here. We still only looked at terms that were multiples of the last term. Okay, and we got our values. It's important to know though that you need to consider the multiples of the leading coefficient as the denominator if you can't find it with the numerators alone. Okay, no questions there. Number 4. So here's an example, guys, where factoring doesn't work. Okay, so we have this equation. It says solve each of the following. So we move the -1 over to the other side. We have this equation now. And we use factor theorem. And the only ones we can test here, we have no leading coefficient of the largest degree. So we test 1 and -1. Both of those values give us a 7. So in this case, we don't have any whole number factors. Okay, we don't have a quartic formula. So we can't solve this. So we're stuck. Okay, the only thing we can do is make estimates about the graph. Okay, we know because it's an even exponent, we know the end behaviors are the same. Okay, because it's a positive coefficient, we know that they both go up. Okay, and then finally we can figure out the y-intercept. If we sub in x equals 0, we know the y-intercept is 1. Okay, so we can make this 1 and then this behavior. That's the best we can do. Okay, we don't know the zeros. Okay, and there happens to be none that exist. Okay, it's not always the case. It's not always the case that none exist when we don't know them. Here we have an example. It's a cubic function. Again, we guess and test 1, -1, 3, and -3, none of which give us 0. No zeros. So we don't know. So we can only make estimates about the end behaviors. We know it's odd and positive, so we know this goes up and this goes down. And we can figure out the y-intercept, which is 3. Okay, but we don't know this point. Interesting to look online and see if there is a cubic equation, right? I'm pretty sure there would be. So finally, summary. The solutions to a polynomial equation f at x equals 0 are the zeros of the corresponding polynomial function. This is just factor theorem, right? Polynomial equations can be solved using a variety of strategies algebraically, which is, really the only one we use. Only some polynomial equations can be solved by factoring. Since not all polynomials are factorable, in these cases, graphing technology must be used, or only estimates about end behavior and behaviors and y-intercept are known. When solving problems using polynomial models, it may be necessary to ignore the solutions that are outside the domain defined by the conditions of the problem. So example, radius cannot be negative. And last point I want to add, I'm not sure why it's not here, when using factor theorem, you need to test P over Q, where P is factors of the constant and Q is factors of the leading coefficient. Any questions?